Hello everyone, welcome back to my channel. Today, we're diving into the world of structural engineering as we uncover the reasons behind the recent maintenance on the K-10 Kill Creek Bridge in Soto, Kansas. The K-10 Kill Creek Bridge connects Lawrence and Overland Park and was constructed back in 1975. Recently, structural engineers conducted a thorough inspection and discovered some concerning issues that needed immediate attention on the both westbound and eastbound bridges. The westbound bridge was rehabilitated last year, and the eastbound was done recently this year. In this video, I am going to talk about the structural issues and its solution for the eastbound bridge. The following issues were found on the eastbound bridge as shown in the picture. 1. The cracks on the crossframe. 2. The gap in between the girder and the concrete deck. Okay, let's try to explain each issue in brief. First one, the crack on the crossframe. When observed by the structural engineers, the crack on the crossframe did not look like a traditional fatigue crack, which is usually from cyclical truck loading and differential settlements between girders. In our case, cracks looks to have originated due to longitudinal thermal contraction and concrete binding components that are not usually part of the traditional fatigue crack. As the original deck and girders of the bridge were not made composite with the use of headed shear studs, girder and slabs were able to move independently during thermal expansion, except for at the top of the abutment crossframe, which is embedded in the slab. A gap is visible in the picture in between the deck and the girder. This means that forces due to differential thermal expansion in the concrete deck and steel girders are transferred at the abutment crossframes. This cyclical thermal loading is the most likely cause of the large crack in the crossframe. But when you zoom in on the image at the top of the weld to the stiffener, a half-inch or so long crack is formed in the weld as well. Okay, what could be its solution? Let's talk about the solution now in points. 1. Replace the abutment crossframes and bearing stiffeners. 2. Use bolted connection rather than welded connection. 3. Use headed shear studs for making the bridge composite. Okay, now let's briefly explain the solution. To address this crack issue in this bridge and other modern rolled beams and welded girder bridges, headed shear studs are used. The shear stress is evenly distributed along the length of the top flanges between the deck and the superstructure by making them composite using shear studs. This reduces the shear force in any one location and improves performance by increasing the effective depth of the flexural member by using the deck and reinforcement as additional top flange area. We also avoided welding crossframes to stiffeners and used bolted connections, which are less likely than welds to concentrate stresses. By also replacing the abutment-bearing stiffeners, we are ensuring that we aren't missing cracks or warping in the existing stiffeners and welds that would continue to concentrate forces after we replace the frames. So, in order to make sure the bridge is structurally strong to carry the loads, we first demolish the deck, add the headed shear studs on top of girders, replace the deck and the approach slab, reset the bridge bearing, and paint the girder. I hope I am able to provide you some knowledge on the issues and rehabilitation techniques of the K-10 Kill Creek Bridge. I'm currently working on the detailed steps and procedure we followed during the project. Please stay tuned for that. This is all for today. Thank you, and have a great day.